CT Physics and Imaging, A Guide for Technologists, Chapter 4, Data Acquisition. Patient conversations are sometimes predictable. Here's one common scenario. Patient, quote, "I'm here for my CAT scan, so where's the cat?" Patients are so funny. There are several ways to conceptualize the CT image production process, none of which involves cats. It might be helpful to reduce the process to 3 general steps. Step 1, inputs, the data acquisition. Step 2, processing, called reconstruction. And step 3, outputs, which is the image display. Think of the input, or data acquisition, as all of the physical and technical parameters that go into creating the scanned data. Processing, that's reconstruction, is the series of events used to transform this data into useful image information. Finally, this processed data is displayed in the same way as other digital images, as pixels within a matrix that can all be manipulated in various ways. The focus of this chapter is data acquisition and the variety of input variables that go into creating the initial scanned data. Imaging axes. In CT, it's very important to think of the patient as a 3-dimensional object. That's because the patient is a 3-dimensional object and because the data created in CT includes all 3 dimensions. This is obviously different from general radiography, which produces 2-dimensional images where all of the anatomy is superimposed onto itself. The 3 CT imaging dimensions are the x-axis, y-axis, and the z-axis. The x-axis, or x-plane, extends horizontally across the scanner, representing data coordinates in terms of right and left. The y-axis, or y-plane, extends vertically across the scanner, representing data coordinates in terms of anterior and posterior. The z-axis, or z-plane, extends longitudinally through the scanner, representing data coordinates in terms of superior and inferior. Figure 4.1. CT scanners create 3 dimensions of anatomical data. The x, y, and z axes all influence the final image. The x-axis defines the data from right to left. The y-axis defines the data from anterior to posterior. And the z-axis defines the data from superior to inferior. Why do these axes matter? The data produced by a CT scan is actually one large cylinder of data divided into tiny cubes of information called voxels, a volume pixel. Each voxel represents a very specific point in the patient that can be identified by its location in each of these axes. The z-axis location represents the specific slice, and the x and y coordinates represent the location within the slice. The exact center of the CT scanner is sometimes called the isocenter, which is the midpoint of the x and y axes. Ideally, the anatomy of interest should be positioned in the isocenter. This ensures the radiation exposure is equal in all directions. Most scanners use laser lights that converge at the isocenter. Field of view. There are 2 fields of view in CT. The scan field of view, that's the SFOV, and the display field of view, the DFOV. The scan field of view, or SFOV, refers to the entire area inside the scanner that is actually being scanned. The display field of view, or DFOV, refers to just the area that is processed for viewing. Not all scanned data collected during the imaging procedure is actually processed for viewing. Only the data within the display field of view, set by the technologist, is processed and displayed as the image data. The entire data set from the scan field of view is saved on the CT computer as raw data, but it is not processed and it cannot be viewed without retrospectively reprocessing the scan. Any area outside of the scan field of view is not scanned and cannot be viewed. The relationship between the SFOV and the DFOV is represented in Figure 2.4. Figure 2.4. The scan field of view, in gray, is the entire area scanned during the procedure. The display field of view, in black, is the area within the scan field of view that is actually processed for viewing. Any part of the patient outside of the scan field of view is not scanned at all, and no data can be retrieved. The display field of view, DFOV, is set by the technologist based on the localizer images. It can be made larger or smaller, depending on the size of the patient and the anatomy of interest. The scan field of view can be set by the technologist, but less options are available. General Electric, that's GE, scanners have just 2 scan fields of view. The large, which is 50 centimeters, and the small, which is 25 centimeters. Any area within the scan field of view can be recovered through retrospective reconstruction, even if it's not initially included in the display field of view. Once the original scan data is removed from the computer, this would be impossible. Here's a case study. Clipping the lungs. After completing a CT of the chest, you notice that your DFOV does not include the entire lung field. Is there any way to retrieve the missing information, or should you just plan on offering your head to the radiologist? Here's the solution. There is a way, as long as the missing information is still within the scan field of view. A technologist who values his or her head should retrospectively reprocess the images and open the display field of view to include the entire lung field. If the lung fields are outside of the scan field of view, which is unlikely, there is no way of retrieving the missing anatomy. Scan type. CT has 3 distinct scanning modes: axial, helical, and volume. The resulting images look virtually identical, but the scanning processes are very different. Axial scanning. This is the oldest mode of CT scanning, but it continues to be a valuable scanning mode for numerous protocols. Axial scanning is also called sequential scanning because the data is collected one section at a time. When the scan is initiated, the tube and the detectors rotate around the patient and acquire the first section of data. Next, the patient table slides forward and the next section is acquired. Axial scanning is not a continuous exposure. The X-ray exposure and the data collection process pauses while the table moves the patient to the next position. Figure 4.3. Axial mode uses a step and shoot method in which the scan data is acquired one section at a time. After each rotation of the tube, the X-ray exposure pauses while the table moves the patient to the next position. The amount of data collected per tube rotation during axial scanning depends on the number of activated detector rows. For example, if the scanner is using 16 detector rows and each detector row is 1 millimeter wide, the scanner is collecting 16 total millimeters of data per section. After scanning the first section, the table moves 16 millimeters and scans the next 16 millimeter section. Helical scanning. This is the most common mode of scanning. Routine images of the chest, abdomen, pelvis, angiography protocols, and most extremities are scanned using helical mode. Figure 4.4. Helical mode uses a scanning pattern that looks like a spiral or helix around the patient. The patient table and the tube are in continuous motion during scanning. Helical scanning, also called spiral scanning, receives its name based on the path the X-ray tube takes around the patient. The shape of the data acquisition pattern, in Figure 4.4, has the appearance of a helix or spiral. Unlike axial scanning, which acquires one section of data at a time, a helical scan captures one large spiral of data while the tube and the table are in constant motion. The major benefit of helical scanning is decreased scan time. Axial scanning has several stops and starts, but helical scanning gets all of the information without stopping. This adds to patient comfort by reducing the number of breath holds during the scan. But the more important effect relates to contrast administration. Intravenous contrast is quickly diluted in the bloodstream and is rapidly removed from circulation by the kidneys. This means there is a very small window of time during which the contrast can be viewed in the organ of interest. Case study: helical malfunction. A CT of the chest with contrast is requested, but the helical mode of your scanner is not functioning. Could the axial mode be used for the scan? Here's the solution. Don't even try. When iodinated contrast is injected intravenously, it will fill the vasculature of the chest within 30 seconds, and be nearly gone within 60 seconds. Helical scanning allows the chest to be imaged rapidly during peak contrast enhancement. Axial scanning would not be finished in time to view the contrast while it's still concentrated in the chest. Volume scanning. The only scanning mode requiring no table movement is volume scanning. This is only possible with scanners using a large number of detector rows, 250 or more. All scanning modes create a volume of data, but this scanning mode images the entire organ of interest in just one rotation of the tube. There's no table movement and no additional sections needed. Figure 4.5. Volume mode acquires the entire data set in just one rotation. There is no table movement and no additional sections. This mode requires that the detector array be at least as large as the organs being scanned. So how is this possible? There's no special technology except that the detector array has to be large enough to include the entire organ being scanned. For example, Toshiba's 320 slice Aquilion 1 can easily collect the scanned data for the entire head or entire heart in just one rotation of the tube. The major benefit of volume scanning is rapid scanning with minimal motion. Acquisition rate. How fast is a CT scan? It depends entirely on the input variables set by the technologist. There are 3 simple ways to decrease the total acquisition time, all of which must be balanced with image quality. Rotation time. The time required for scanning can be decreased simply by decreasing the tube rotation time. The upside is a faster scan and a potential to decrease patient motion artifacts. The downside is an increase in image noise, assuming there's no change in MA or the number of projections per tube rotation. Acquisition thickness. The thickness of each detector row is called the acquisition thickness. Detector rows can be functionally combined to increase the acquisition rate or decrease the total scan time. Here's an example. 2 detector rows that are 0.625 millimeters wide can be combined to function as one detector that is 1.25 millimeters wide. With these detectors combined, they need less radiation and less time to produce minimal image noise. There are numerous ways to configure the acquisition thickness with the same total beam width. 0.625 millimeters times 16 rows equals 10 millimeter beam width or beam coverage. 1.25 millimeters times 8 rows equals a 10 millimeter beam width or beam coverage. Finally, 2.5 millimeters times 4 rows also equals 10 millimeter beam width or beam coverage. The total beam coverage is the same, 10 millimeters, and the entire detector array is being used, but the acquisition thickness is different. So, should we always use a large acquisition thickness? No. There are image quality losses when increasing the acquisition thickness. As acquisition thickness increases, spatial resolution decreases in the z-axis, and partial volume averaging increases. Partial volume averaging is a loss of tissue visibility when different tissue types are averaged together within a slice and displayed with the same Hounsfield units. When selecting the acquisition thickness, remember that this is the limiting factor for reconstruction thickness. The reconstruction thickness can be larger than the acquisition thickness, but usually not smaller. This concept is discussed further in Chapter 5. Figure 4.6. The acquisition thickness of a 16-row detector can be changed by combining adjacent rows together. 0.625 millimeters times 16 rows, or 1.25 millimeters times 8 rows, and 2.5 millimeters times 4 rows. Figure 4.7. Scanners using non-uniform detector rows do not have thin slices on the outer rows. As a result, high-resolution scans can only be performed using the inner rows. This image shows multiple combinations that result in 4 rows of data. Notice that the thinnest slices are only available in the inner 4 rows. Scans using a wider beam for faster speeds must use a thicker acquisition thickness. Case study: new protocol design. A radiologist asks you to design a new high-speed CT chest protocol to be used on infants and other patients who cannot control their breathing. What acquisition thickness would you suggest for your 32-slice Toshiba scanner? Assume it uses a uniform detector array with 0.5 millimeter detector elements. Here's the solution. A high-speed scan requires a large acquisition thickness. In this case, combining 4 rows into one would suffice. 0.5 plus 0.5 plus 0.5 plus 0.5 equals 2 millimeter acquisition thickness. That results in 2 millimeters times 8 slices and still uses the entire width of the beam. Pitch. If you found the last section a little exhausting, you might want to pause and go drink a caffeinated beverage. Ready now? Pitch is a variable applying only to helical scanning. Pitch is a ratio describing the distance the table moves during scanning compared to the beam width. Since the table does not move during the exposure within axial and volume modes, it makes sense that this only applies to helical scans. Just like the rotation time and acquisition thickness, pitch affects the speed of the scan and influences spatial resolution of the resulting images. A high pitch results in a faster scan with lower resolution images. A low pitch results in a slower scan but with higher resolution images. Calculating pitch is very simple. Pitch is equal to the table movement divided by the beam width. If the table movement and the beam width are equal, then the pitch is equal to 1. If the table movement is greater than the beam width, the pitch is larger than 1. If the table movement is less than the beam width, the pitch is less than 1. Figure 4.8 provides examples of how changes in pitch affect the shape of the spiral around the patient. Figure 4.8. These images are in order of increasing pitch. As the pitch increases, the table moves more with each tube rotation. When the pitch is greater than 1, gaps in information start to appear. So why does pitch matter? If the pitch is less than 1, there is overlap in the helix and the scanner is getting extra views of each body section. This results in a very slow scan with very high spatial resolution. If the pitch is equal to 1, there is no overlap in the scan, but there is no missing views either. This is the standard for most protocols. If the pitch is greater than 1, there are missing views in each body section. This results in a faster scan with lower spatial resolution. We can also use pitch ratio to calculate how much the table is moving with one rotation of the tube. For example, if the beam width is 10 millimeters and the pitch is 1.5, how much is the table moving per tube rotation? It's a simple calculation. The table movement is equal to the beam width times the pitch. Inserting the variables provided, that's 10 millimeters times 1.5 equals 15 millimeters of table movement per tube rotation. The more the table moves, the faster the scan will be. Case study, pitch and anatomical coverage. Consider these two scan settings. Scan A is set up with an 8 by 1.25 millimeter detector configuration and a pitch of 1.0. Scan B is set up with a 6 by 2.5 millimeter scanner configuration and a pitch of 0.666. Which scan setting will result in the most anatomical coverage per tube rotation? Here's the solution. Suddenly, you feel like you know nothing about pitch? The answer is that both scan settings result in the exact same amount of anatomical coverage. Start by calculating the beam width for each scan. For scan A, 8 by 1.25 millimeters equals a 10 millimeter beam width. Scan B, 6 times 2.5 millimeters equals a 15 millimeter beam width. The total anatomical coverage is calculated by multiplying the beam width by the pitch. Scan A, 10 millimeters times 1, which is the pitch, equals 10 millimeters of coverage per rotation. Scan B is 15 times 0.666, also equals 10 millimeters of coverage per rotation. As evidenced by the previous case study, all the variables of data acquisition are interconnected in various ways. Changing one often results in changes to the others. When the technologist makes a change, he or she should do so with an understanding of how that change might influence the scan speed, spatial resolution, image noise, and patient dose. Here's one more case study to test and stretch your knowledge of data acquisition factors. Case study, total scan time. Calculate the total scan time for an imaging procedure set with these variables: 0.8 second rotation time, 1.26 pitch, 16 by 1.125 detector configuration, and a total scan length of 600 millimeters. Solution. Start by calculating the beam width by multiplying the number of detector rows by the detector acquisition thickness. That's 16 times 1.125 millimeters, which equals 18 millimeters. Next, calculate the anatomical coverage per tube rotation, or table movement, by multiplying the beam width by the pitch. That's 18 millimeters times 1.26 equals 22.68 millimeters. That's the total amount of anatomy scanned in one rotation. So how many rotations will it take to cover the entire scan length? Divide the total scan length by the coverage per tube rotation. That's 600 millimeters divided by 22.68 per rotation, which equals 26.45 rotations. Finally, multiply the number of required rotations by the rotation time to get the total scan time. 26.45 rotations times 0.8 seconds per rotation equals a total scan time of 21.16 seconds.